So you are now aware as how the concept of convolution works on the input images. Now to recall about this important concept, let's consider this example guys. I'm having an image. Now let's say this image is having the dimension as 30 by 30. Now if you look at the components that I'm sending for my convolution operation, so I'll be using the component of kernel size. So this kernel size is nothing but the weight matrix which we will place on top of the input image. So in my current example, I have written as kernel of 3 by 3. So this would mean this is a kernel and this is of the shape 3 by 3. And what we will do is we will place this kernel on top of this input image, and we are going to slide from left to right and top to bottom to perform the convolution operation. And now you already have an intuition as what this convolution operation is. So this convolution operation is nothing but finding the output, which is nothing but the finding the dot product between the image pixels of that region with the weight matrix to get the required output. So that's what we know already. And along with that, you also have an intuition as what this pooling layer means as well, isn't it? So you have learned about the average pooling as well as the max pooling in your previous class. So in this video, we are going to extend this concept of convolution operation, and while performing the convolution operation, the next step that we are going to do over here in this video is we are going to apply the activation on each of the convolution operation. Now to understand the same, here I have defined my input shape as 1, 5, 5, 1, and you know already what are these individual component means as well guys, so I'm not going to explain it. And here I have written my x as tf.random.normal of input shape, so this is generating a tensor object with the shape of input shape. And as a next step, I have defined my L1, which is a conv2D layer, which has the number of filters as 1, kernel size as 3, 3, padding as valid, and input shape as input underscore shape 1 colon blank, which is nothing but 5, 5, 1. So height, width, and this one is number of channels guys. And here if you observe, I have written as use underscore bias as true. So this is what I have written guys. So this would mean that if I am performing the convolution operation, what the system will do is for each of the region, the system is going to take the dot product between the this weight matrix with my input image of that region. It is going to add it with bias term. So that is what it says guys. So let me just execute this. So if I just execute this, I have the resulting output of y as 1, 3, 3, 1. So we have lost a dimension because I have mentioned my padding as valid. Okay. Now if I display my x, so this is my input which I have used actually. So this is how my input looks like, which has the shape of 1, 5, 5, 1. And if I display my y, so this is having the shape as 1, 3, 3, 1. So this is how my output y looks like. Now here in this cell, I am performing the mathematical operation in a manual manner. So I'm extracting the weights. To extract the weights, we just specify the layer name and use this get underscore weights method guys. And I am using the 0, that is I'm mentioning the index as 0 to extract the weight terms. And here I have written as b is equal to l1.getWeights, and inside the indexing operator, I have mentioned the index as 1. So this will extract only the bias term. And after that, here I am flattening out my input. So to flatten out my input, so as a first step, I'm just extracting the first 3 by 3 guys. So if I have a matrix, so in this case, I have an image of the size 5, 5. Okay, and on this image of 5, 5, I'm extracting only 3 by 3 components. So to extract the 3 by 3 components, I have written as tf.reshape x colon 3, colon. So this is going to extract only 3 by 3 region of my 5 by 5 matrix, which is nothing but my input image. And here I am performing the reshape of this input comma -1. So this is going to flatten out my input image, guys. And this flatten out or this flattened input image will have the dimension as 9 because I'm just extracting this 3x3 region of my 5x5 image. And in the same way, I'm flattening out my W values. So I have written as tf.reshape w comma -1. After that, I'm performing the dot multiplication, that is here I've written as tf.tensor.xflat comma wfat, and then I'm mentioning my axis as 1. So this is going to perform the tensor dot operation, and then I'm adding the bias term, guys. So let me just execute this. So we have the output that says as minus 0.1414. And if you observe over here, in my output of y, I have the same value. Now to get the better visualization, let me display my b, guys. So if I display my b, the value of bias term will get outputted. So the value of my bias term is 0. So in my case, it is 0, but depending on the initialization that we use in our future classes, this b weights can vary, but the way this is going to work, it's just like that we are seeing over here. It is going to perform the dot product between the input image of that region with the kernel of that region, and it is going to add the bias term on top of it. Okay. Now, let's see what happens if I apply the activation on top of this output, guys. Now observe over here. Here I have used the same input image and I'm defining my x as a tensor object with those initialized values. I'm applying this conv2d operation, and this conv2d layer has filter as 1, kernel size as 3,3, padding is valid, and observe over here. Here I am performing my activation as ReLU. Okay. So along with everything that I have applied previously, I'm adding one more additional term, that is activation as ReLU. And after that, I'm applying this L1 layer on my input image X. And finally, I'm displaying my output of Y. So let me just execute this. So if I just execute this, I still have the output as 1, 3, 1. And if I display my X, this is how my X looks like. Okay. And if I display my Y, this is how my Y would look like. Okay. Now, observe this. This is very important, guys. Here in this cell, I'm just mathematically computing the output just like we did before, guys. So W, so this is going to extract my weights. B, this is going to extract the bias term, and X flat. So this is going to extract the 3x3 region of my input image, and it is going to flatten it. And W, it is going to flatten out my weights vector. And then I'm going to perform the dot product between my input region with my weights kernel along the axis as 1, and for this I'm adding my bias term. So if I just execute this, I have the output as minus 0.68. Now what is this activation means? So let me just show you in a visual understanding as how this activation works, and then we are going to execute this particular cell, guys. So I'm having an image, and this image is having the shape as 5x5, and on top of this image I am placing my kernel, and this kernel is having the shape of 3x3. So what I'll do, I'll perform the dot product between the input image of that region with kernel values, that is the initialized weight terms. So I'll write it over here as dot product of input with weights term. Okay, after I perform the dot product, this is going to return me the output. But here, if you observe, I had written as activation is equal to ReLU. So that means whatever the output that I get, so let me just highlight this. So whatever the output that we get as a result of applying this dot product operation, we are going to apply the activation function on the resulting output. So my activation will be applied on top of this output. So the resulting values will be the resulting outcome of this activation layer, guys. So let's test it out. So here I'm applying my ReLU activation function on top of my previously output, that is tf.tensor.x flat comma w flat comma axis is equal to 1. So let me just execute this. So if I just execute this, I have the output as 0. We have the output as 0 because I am performing I am applying this ReLU activation function. The way it would work is, the ReLU activation function, if you remember previously in our starting classes, I had explained that the ReLU function has the function that says as max of 0 comma x. So if the value is less than 0, the output will be 0. And if the value is greater than 0, at that time it is going to return the x itself. Okay. In our case, since the value of my outcome or my value of my output is less than 0, this is returning the value of output as 0, guys. And we can observe the same over here as well. See, the first output as a result of applying this ReLU activation function on top of our 3x3 kernel is 0. Okay. Now for the sake of completion, here in this cell, I am performing the activation of sigmoid. So let me just execute this cell. See, instead of ReLU, I'm just applying the activation of sigmoid. So if I display my X and Y, this is how my X and Y looks like. Now here, I'm extracting my weights, bias term, I'm flattening out my input X of 3x3 region. I'm flattening out my W, that is weights kernel, and I'm performing the dot product. So if I just execute this, this is the output of this is the output for performing the dot product, that is minus 0.03. Now on top of this, I'm applying the sigmoid function. So tf.nn.sigmoid, and I'm just inserting the previously generated output, that is tf.tensor, that is this term. So if I just execute this, I have the output as 0.490, and if you observe over here, see, that's the same value that we have as an output as a result of applying this con2d layer with kernel size of 3,3, padding as valid, bias as true, and sigmoid activation layer. I hope this entire series of classes that we have took till now gave you a clear understanding as how this convolution operation works from scratch, guys. So we started our series of this convolution layer by defining the input image from scratch. So we defined our input matrix of 5x5, and using that input image of 5x5, we have learned each and every component that we are sending inside this con2d layer. Now in our further classes, we are going to use this understanding of con2d layer and implement it for the real world data set. I hope you guys are as excited as I am, and I look forward to seeing you in the next class.